The internet has a secret number. You don't know it. The engineers who built it do. And the second that number hits 0, your Spotify stops. Your texts don't send. Your bank forgets you exist. It's not a password, it's not a server count, it's a single integer, and it's hiding inside the shape of the network itself. Here's what I want you to imagine. You're a network engineer. You've just been handed a map of every cable connecting every major internet hub in the country. Hundreds of nodes, thousands of connections. And your boss says, how many cables would a hacker need to cut, just cut, to split the internet in two? Most people's instinct is a lot. There are thousands of cables. You'd need to destroy half of them. That instinct is wrong. Sometimes catastrophically wrong. One cable, one cut. That's all it took. And the reason comes down to a number so simple it fits in a single variable, baked into the structure of every network, whether the engineers plan for it or not. This is called the connectivity of a graph, and once you see it, you will never look at a network the same way again. Here's what's actually going on. Any network can be modeled as a graph. Dots and lines, nodes and edges. Buried inside that shape is one question. How fragile is this? The answer is called the vertex connectivity, written kappa of G. And understanding it requires one of the most beautiful theorems in all of graph theory. First, connected means you can travel from any node to any other by following edges. No teleportation, just edges. Pretty humble definition for something that runs your entire life. Now, the vertex connectivity, kappa of G, is the minimum number of nodes you'd need to remove to break that connection, to split the graph into two isolated islands. Not edges, nodes. Pull out the right nodes, and their edges disappear with them. That's the sharper question. Think of it like this. Imagine a city's water supply. The pipes are edges. The pumping stations are nodes. The connectivity number tells you how many stations an enemy would need to destroy to cut off the water entirely. That's not an abstract question. Cities calculate this. Now here's where it gets beautiful. In 1927, a mathematician named Carl Menger asked a different question about the same structure. Instead of asking how many nodes you need to remove, he asked, how many independent paths exist between two nodes? Independent paths. Paths that share no nodes in common. Completely separate routes from A to B. And his theorem says this. The maximum number of independent paths between any two nodes equals the minimum number of nodes you'd need to remove to disconnect them. Read that again. The number of escape routes equals the number of blockers you need. It's a perfect duality. You can't increase the attack without the defense responding, and you can't strengthen the defense without creating another escape route. This is Menger's theorem, and it is exactly as clean as it sounds. There's also edge connectivity, lambda of G. Cut edges instead of nodes. And kappa, lambda, and the minimum degree delta satisfy one of the cleanest inequalities in graph theory. Kappa is less than or equal to lambda, which is less than or equal to delta. In plain English, the hardest attack is always removing nodes. The easiest attack targets the least connected point, and edge cuts fall in between. This is Whitney's inequality, and it tells you, structurally, where every network is most vulnerable, before a single cable is ever cut. Here's the thing nobody mentions. Every real network has engineers who optimize for this number. More redundancy, more paths, harder to kill. But redundancy costs money. So every network is a negotiation between connectivity and cost. And somewhere in that negotiation, someone chose a number. The Taiwanese cables cut in 2023 had their kappa reduced to near zero for an entire region. Not a math failure, a budget decision made years before. Graph theory doesn't just describe networks, it predicts exactly where they break. That number, it was calculated, argued over. It was Carl Menger's question from 1927 about paths and cuts and the exact cost of resilience. Every network you trust with your life has a kappa, a fragility score, a secret number. Now you know what it means.